A pleasant day to everyone, to my blockmates, intersurgeonal. Now we will talk about the nuclear chemistry and radioactivity. Now, let us first discuss the nuclear activity. The nucleus does not strongly affect the chemistry of the atom, whether bond making or breaking. However, the nucleus can undergo changes, which usually cause an element to change into another element. So if there is a changing, we can say that it has a nuclear activity. Now, the second one, the implications of nuclear activity for humans. Hazardous affects the radiation. That is the first one. So, as we know, radiation can damage the inner inner body, which is in the specific area. It is in the DNA in our cells. And the second one, the medical applications of radioactivity. Nuclear medicine procedures are used in diagnosing and treating certain illnesses. These procedures use radioactive materials called radiopharmaceuticals. Third one, dating by radioactivity. So as we know, the dating, as we know, it is about the two couples, but it is not. The radioactive dating is a method of dating rocks and minerals using radioactive isotopes. This method is useful for igneous and metamorphic rocks, which cannot be dated by the stratigraphic correlation method used for sedimentary rocks. The fourth one is the nuclear energy. As it applies to nuclear energy, many materials created during the operation of a reactor, are radioactive. As they decay, they emit radiation. So that the energy that they carried by the radiation is often sufficient to cause damage to biological cells and is therefore a health risk. And the last one, nuclear weapons. So here the radioactive can make nuclear bombs, release their energy in the form of a blast. So as we know, it will go boom, or in other words, it will blast. So a fireball, visible light, and radioactive ionizing are present. Now, let us know the what is the radioactivity. So radioactivity, this is the spontaneous decompositions of atomic nuclei, which releases high energy particles or rays. Radioactive decay results in a different nucleus, like the nuclide, a nucleus with specified number of protons and electrons. So it is equals to the specific isotope. So materials that emit radiation, like the alpha, the first one, second one is the beta, and the gamma, are called radioactive, or the radioactivity comes from the atomic nucleus and not from the electron cloud that surrounds the nucleus. Now the next one, we're gonna discuss the isotope symbol. We will review the past lesson. What are these parts? As here, the illustration, the X is the element symbol. Um, um, Noted, no, there is no X in the element in the periodic table. This is an illustration only. So X is the element symbol, and the A is the mass number, or the number of protons added by neutrons, and the Z is the atomic number, the number of protons it identifies in the element, which is the atomic number. Now, like the similar notation of subatomic particles, like the proton, the 1, which is P, and the neutron, it has the 0 and 1, and the electron, -1 and 0. Now, radioactivity, every element has at least one isotope whose nucleus spontaneously decomposes, that what we call radioisotope. A certain level of radiation naturally occurs all around us, even in our bodies, like the potassium. Like this, in the illustration, the parent nucleide and the daughter nucleide. There's the daughter nucleide. Um, this helium here is it is given na po siya. Then the isotopes in which the number of protons and neutrons are balanced are stable. So it should be balanced and stable. In the lighter elements, this balance occurs when the numbers of protons and neutrons are approximately equal. Now, this is the nuclear equations. As we can see, this is the carbon. So, as we know, the atomic number of carbon is 6, and it has the atomic mass of 14. So, as given by, it has a 14. And then yields to the nitrogen, the 7. And why? If this carbon will added by 1, so the next one of the periodic table, in the periodic table, the element is nitrogen. So the atomic number of nitrogen is 7. Then when we divide 14 divided by 7, it is equals to 2. Now, when we multiply 7 times 2, it is equals to 14. So, it is equally distributed and added by the electron into the negative 1 of 0. Now, in a balanced nuclear equation, both the atomic number and the mass number must be conserved. So, both of them must be equal and balanced. So, if there is a serious imbalance in the proton to neutron ratio, either too few or too many neutrons, a nucleus will undergo a nuclear reaction to make the ratio more favorable, and the nucleus will be more stable. So that is it. Why na ang 6, which is the carbon, na nalipat po siya into nitrogen, which is kasunod po ng carbon is the nitrogen, which is the atomic number of nitrogen is 7. Now, furthermore, to understand, so there are types of radioactivity. First one in our list, it is the alpha particle emission, or the symbol of this is small letter A. As we can see, the here the illustration. For example, the radium is yields to the helium of 4 and 2. The 2 is the atomic number, and the mass is 4, and added by 218 and 86 radon. So why is it? So as further in learnings, alpha particles are helium nuclei. So there is an helium attaches to one of these element or two elements. So each contains 2 protons and 2 neutrons. Each has an atomic number of 2 and a charge of 12. Now, here the example, a particle, helium nucleus, which is the He42. So, the net effect, loss of 4 in mass number and loss of 2 in atomic number. So, as you can see here in our illustration, the 202 subtracted by 4, it is equals to 218. Now, the radium, which is in the 88, its atomic number is 88, and subtracted to 2, it will become 86. Now, we will go back. We will backward. Like kanina, we forward in one step. Like we will backward two step. So the radium, barium, and radon. So the 86 in the atomic number in the periodic table is radon. So this is correct. Now here the example, second example, the thorium, and you subtracted it into 2 will become 88, which is the radium. So that is easy one. And next, the second type is the beta particle, or the unit of this is like capital letter B, and these beta particles are electrons. Each has a charge of 21. If there is a serious imbalance in the proton to neutron ratio, either too few to many neutrons, a nucleus will undergo a nuclear reaction to make the ratio more favorable, and the nucleus will be more stable. Now, the proton remains in the nucleus and the electron is emitted from it. The emitted electron is called a beta particle, and the process is called beta emission. Like for example, the phosphorus is 15 in the atomic number of phosphorus is 15. For example, is a beta emitter. A phosphorus, which is 15 atomic number, the atomic number is 15, nucleus has 15 protons and 17 neutrons. So it has it is not equal or stable because it has 15 protons and 17 neutrons. The nucleus remaining after an electron has been emitted now has 16 protons and 16 neutrons. So we added the phosphorus 1 forward para maging equal. Now, its atomic number is increased by 1, but its mass number is unchanged. So, likewise, like the alpha, we subtracted the 2, which is the atomic mass and the atomic number. In here, the beta, we added only the atomic number, but it remained the atomic mass. Now, its atomic number is increased by 1, but its mass number is unchanged, like I've said. The new nucleus is therefore sulfur 32. Thus, when the unstable phosphorus 32, it has 15 protons and 17 neutrons. And when it is converted to sulfur 32, which has the 16 protons and 16 neutrons. So 16 plus 16, it is equals to 32. So now the nuclear stability is achieved.
Next is the gamma ray emission. Although rare, some nuclei are pure gamma emitters. Gamma ray are high-energy photon of light and it has no charge or mass. Gamma emission often accompanies alpha and beta emissions. Both alpha and beta emissions can be either pure or mixed with gamma rays. In this equation, boron 11 symbolizes a boron nucleus in a high energy or excited state. In this case, no transmutation takes place. The element is still boron, but its nucleus is in a lower energy or more stable state after the emission of excess energy in the form of gamma rays. When all excess energy has been emitted, the nucleus returns to its most stable, lowest energy state. Basically, there is no change in mass or atomic number. Following the gamma ray emission is the positron emission. A positron is a particle that has the same mass as an electron but has a charge of positive 1 rather than a negative 1. Positron emission is much more rare than alpha or beta emission. Because a positron has no appreciable mass, The nucleus is transmuted into another nucleus with the same mass number but an atomic number that is 1 unit less. For example, is sodium 22. In this balanced nuclear equation, the mass number on the left and right are 22. The atomic number on the left is 11 and that on the right is 10. In electron capture, abbreviated as EC, one of the inner orbital electrons is captured by the nucleus and there reacts with a photon to form a neutron. Thus, EC reduces the atomic number of the element, but the mass number is unchanged. Mercury 201, for example, decays by electron capture to give gold 201. So this is the summary of the radioactive decay processes. We have the process and its corresponding symbol, and then we have the changes in atomic number, mass number, and number of neutrons for each process. In alpha particle emission, the change in atomic number is -2, the change in mass number is -4, and the change in number of neutrons is -2. In beta particle emission, the change in atomic number is +1, the change in number of neutrons is -1, and there is no change in the mass number. In gamma ray emission, there is no change in the atomic number, mass number, and number of neutrons. In positron emission, the change in atomic number is -1, the change in number of neutrons is +1, and there is no change in mass number. Finally, in electron capture, the change in atomic number is -1, the change in number of neutrons is +1, and there is no change in mass number. So we have the nuclear transmutation. Nuclear transmutation is the change of one element into another by particle bombardment. The neutron, alpha particle, proton, and nucleus. It happens naturally every time an element gives off a beta particle. Every time a nucleus emits a beta particle, it is transformed into another nucleus with the same mass number but an atomic number that is 1 unit greater. Below are some examples. Most of the 3,300 known radioisotopes are made through artificial nuclear transmutation in particle accelerators. All elements with atomic numbers greater than 92, or transuranium elements, have been artificially made.
As already noted, radioactivity is not detectable by our senses. We cannot see it, hear it, feel it, or smell it. How then do we know it is there? Alpha, beta, gamma, positron, or X-rays all have a property we can use to detect them. When these types of radiation interact with matter, they knock electrons out of the electron cloud surrounding an atomic nucleus, thereby creating positively charged ions from neutral atoms. For this reason, we call all of these rays ionizing radiation. Ionizing radiation is characterized by two physical measurements. First is its intensity, which is the number of particles or photons emerging per unit. Second is the energy of each particle or photon emitted. To measure intensity, we take advantage of the ionizing property of radiation. Instruments such as the Geiger-Müller counter has or contains a helium or argon. In this slide, Geiger-Müller counter is a high-energy particles ionized argon. Argon ions can conduct electricity. This is a picture of a Geiger-Müller counter. In this side, it shows the window where the particle passes, and inside shows the orange particles, which is the argon atoms, and on the left side is an instrument or a speaker which gives click for each particle. Second is the scintillation counter. It uses a substance that gives off light when struck by high energy particles. It also has a material called a phosphor that emits a unit of light for each alpha or beta particle or gamma ray that strikes it. Third is the thermoluminescent dosimeters. Electrons excited by high-energy particles are trapped in crystals, then heated to relax into ground state and emit light. On the right side shows the thermoluminescent dosimeters. Second is the half-life. It is the time required for half of the original sample of nuclei to decay. There are two samples below. First is the 1,000,000 220 nucleons, 86 protons of radon, and in a minute, 1/2 million 220 nucleons, 86 protons of radon, and in 1 minute, there's a 1/4 million 220 nucleons, 86 protons of radon. The second one is a 1,000,000 238 nucleons, 92 protons of uranium. In a 4.5 billion years, it became 1/2 million 238 nucleons, 92 protons of uranium. In another 4.5 billion years is a 1/4 million 238 nucleons, 92 protons of uranium. Third one is the half-life of thorium-238. This diagram, there is a diagram below that shows the half-life of thorium-238. In the diagram, the left side is the number of atoms in millions, and below is years in billions, and the particles, the reddish one, represents 0.10 million atoms. And the half-life of thorium-238 is 14 billion years.
Continuations of this topic, which is the half-life. These are the given problem of half-life of radium nuclides. The first example is the Th or thorium has a 232 mass number and 90 atomic number. And to get this particular mass number, we have to add the atomic number to the neutron. So in nuclides, we have 232 nucleons and 90 protons of thorium. The half-life is 1.4 times 10 raised to the power of 10 years, and the types of decay is alpha. Now, to determine the types of decay, we just have to remember that alpha particles with a charge of 12 and mass of 4 amo interact strongly with matter but penetrate the less. They are stopped by several sheets of paper, while beta particles with less mass and a lower charge than alpha particles interact less strongly with matter. They easily penetrate paper but are stopped by a 0.5 centimeter sheet of lead, and while the gamma rays with neither mass nor change have the target greatest penetrating power. So let's proceed to the uranium-238 decay series. In many cases, daughter nuclides are also radioactive. As you can see in this diagram, it shows the decay series. Now, this one example right here is uranium. You guys have two terms to know that whatever on the reactive side is called the parent isotopes, and whatever on the product side is called the daughter isotopes. Now, in the decay series, the daughter isotopes will then become a parent isotopes. Let's for example here, the thorium is the product of the uranium. Then, the thorium produces protactinium and down to alpha and followed by alpha again. So, as you can observe, the decays decrease the atomic number. And when it comes to lead, the bismuth have a choice Either it's undergone to thallium or polonium, but we notice that it ends at final daughter isotopes, which is lead. Lead is 206, and lead is a very stable non-radioactive. And now we have the applications. The applications have the given problem. Here, 14 nucleons and 7 protons nitrogen plus nucleon and 0 proton, 14 nucleons and 6 protons of carbon plus 1 nucleon and 1 protons of hydrogen is equal to carbon negative 14 made. Now, to get the accurate answers, you just have to subtract the nucleon over the protons of each elements, then add. So, half-life of 14 carbon equals 5,715 years.
Damaging effects of radiation. First, ionizing power. It is the ability of radiation to ionize molecules and atoms. More massive particles have more potential to interact with and ionize other molecules. Second, penetrating power. The ability of radiation to penetrate matter. Smaller particles can penetrate more deeply. In other words, ionizing power refers to how well can it knock out electrons from target nuclei, while penetrating power, it is how far can the ray travel before losing all energy. So there are three types of radiation damages. First, the acute radiation damage, damage to cells resulting from exposure to large amounts of radiation in a short period of time. Second, increased cancer risk. Lower radiation doses over a long period of time can cause damage to somatic cells and increase cancer risk. And the third one is genetic defects, damage to DNA and productive cells that shows effect in offspring. Effects of short-term radiation exposure. A unit that indicates biological damage of radiation, it is called REM or A doses. So 20 to 100 dose, probable outcome decrease white blood cells count, possible increase in cancer risk. 100 to 400 doses, radiation sickness, skin lesions, increase in cancer risk. And 500 dose, probable outcome results to death.
Biological effects of radiations. Typical radiation exposure in US. Typical radiation exposure for a person living in the United States. So 1 millirem is equals to 10 raised to the power of negative 3 rem. So the source and the exposure. So the source, cosmic has 50 exposure. From the earth has 47 of exposure. From building materials has 3 exposure. In human tissues has 21 exposure. Inhalations of air has 5 of exposure. So in total, 50 plus 47 plus 3 plus 21 plus 5 is equals to 126. So next is X-ray diagnosis as 50 exposure. Radiotherapy X-rays radioisotopes has 10 exposure. Internal diagnosis and therapy has 1 exposure. Nuclear power industry, luminous watch dials and TV tubes has 0.2 exposures. Industrial waste has 2 exposure. Radioactive fallout has 4 exposure. So, in total, 50 plus 10 plus 1 plus 0.2 plus 2 plus 4 equals 67. So, in total overall, 126 plus 67 is equals to 193. So, 193 equivalent to 0.193 rem. Next is nuclear medicine application. Radio tracers. So, what is radio tracers? Radio tracers are radioactive nuclides that can be put into organism through food or drugs and be traced for medical diagnostics. So, some radioactive nuclides, their half-lives and their medical application as radio tracers. So, the number before the symbol is the mass number. So, The iodine 131 has 8.1 days of half-life, and the area of the body studied is thyroid. Next is iron 39 has 45.1 days of half-life, and the area of the body studied is red blood cells. Next is molybdenum 99 has 67 hours of half-life, and the area of the body studied is metabolism. Next is phosphorus. Phosphorus 32 has 14.3 days of half-life, and the area of the body studied is eyes, liver, and lumors. Next is chromium 51 has 27.8 days of half-life, and the area of the body studied is red blood cells. Next is strontium 87 has 2.8 hours of half-life, and the area of the body studied is bones. Next is technetium 99 has 6.0 hours of half-life, and the area of the body studied is heart, bones, liver, and lungs. Next is xenon 133. So has 5.3 days of half-life, and the area of the body studied is lungs. Next is sodium 21. Has 14.8 hours of half-life, and the area of the body studied is circulatory system. So Z is sometimes not written when listing nuclides. Next is radio tracers and PET scan. So we can see the picture that the body of a person is going to scan. So that's called a PET scans or positron emission tomography. So what is positron emission tomography? It is an imaging technology in which substances containing positron emitting isotopes are introduced into the body. And example of positron producing isotopes is fluorine 18. So what is fluorine 18? So it is a fluorine radioisotopes, which is an important source of positrons. And 11C or carbon 11. It is widely used for the early diagnosis of cancer. So these radioactive isotopes are attached to glucose. Areas of brain rapidly consuming these radio tracers light up on PET screen. Short half-lives on fluorine 18 has 110 minutes, and carbon 11 has 20 minutes. So it is requires speedy synthesis. Next is nuclear medicine application, radiotherapy. So what is radiotherapy? Radiotherapy, it is a therapy using ionizing radiation, generally provide as part of cancer treatment to control or kill malignant cells. So gamma rays are used to kill rapidly dividing cancer cells. Patients undergoing radiotherapy develop symptoms of radiation sickness such as vomiting, hair loss, and skin burns.
That's all for our report, which is the nuclear energy and radioactivity. And here are our references for our reports, and we depend on it and we cited it properly. So thank you so much for listening to us. I hope that you learned something to our report, and stay safe and God bless.